Okay, we're going to talk about Chapter 7 now, the quantum mechanical model of the atom. You'll get to meet Dr. Quantum in just a little bit, but first we have to talk about waves and the lingo that goes along with describing a wave. So, if we look at a wave, here's a wave, what we see is an upper phase and a lower phase. And the wave function, which is what describes the wave, can either be positive or negative, and the point at which it changes from being a positive function to a negative function is at this line right here called the zero crossing. Okay? So this is all one wave right here. And now let's talk about what a wavelength is. The distance between any 2 points, which are equivalent in the same phase, is one wavelength. So wavelength is a distance. It could be the distance between a crest and another crest. It could be the distance between a trough and another trough. It could be the distance at a zero crossing where it crosses the zero crossing and starts going positive or going up to the next point at which it crosses the zero crossing and begins going up. Each one of these is the same distance, and each one of these represents one wavelength. The amplitude of a wave is the distance from the zero crossing to the peak of a wave. A node is the place where a wave makes the zero crossing and goes from a positive function to a negative function of the wave. Now the question asks, how many complete waves are seen on this wave? Well, if we start right here and go to the next crest, that's one wave. If we start here and go to the next, that's the second wave. And we start here and go to the next, that's the third wave. So there are 3 waves depicted in this segment of a wave. So that's what wavelength is, and that's what amplitude is. Then there is the frequency of a wave, the number of cycles, or wave crests, that pass through a stationary point at a given period of time. If all of these waves took a total of 1 second to pass any given point of the line, so we counted that there were 3 waves in this segment, and the wave passes by in 1 second, we see those 3 waves, or 3 cycles. The answer to this then would be a frequency of 3 cycles per second. The term Hertz, H-E-R-T-Z, is also used to represent cycles per second. Now it's entirely appropriate to talk about light as a wave because it behaves as a wave. And in that context, frequency and wavelength are related. The frequency of a wave times the wavelength is equal to the speed of light. Frequency is given by the Greek letter nu, wavelength by lambda. So lambda times nu equals the speed of light, 3 times 10 to the 8 meters per second. So here's a question. If a red light has a wavelength of 725 nanometers, which would be 725 times 10 to the minus 9 meters, because nanometers is 10 to the minus 9 meters, what is the frequency of this wave? See if you can do this and come back to the video. Okay, the frequency is going to equal the speed of light divided by the wavelength. 3 times 10 to the 8 meters per second divided by 725 times 10 to the minus 9 meters. So that you should have gotten 4.14 times 10 to the 14 cycles per second. We don't use the word cycles when we describe frequency, but we simply put a seconds symbol, abbreviation for seconds, minus 1 or 1 over seconds to represent cycles per second. What is the wavelength in nanometers of light that has a frequency of 6.34 times 10 to the 14 hertz? And as I said, hertz is the abbreviation that we use for cycles per second. So, can you calculate wavelength? Turn off the video and see if you can do it. Alright, here we go. Lambda, or wavelength, equals speed of light divided by frequency. The speed of light is 3 times 10 to the 8 meters per second, and we divide that by 6.34 times 10 to the 14 seconds minus 1, or 1 over seconds. And what we end up with is 4.73 times 10 to the minus 7 meters. And then converting to nanometers, 1 meter equals 1 times 10 to the 9 nanometers. So making that conversion, we get 473 nanometers. Now we're talking about light, and the common way we think about light, of course, is visible light, but there's a whole range of electromagnetic spectrum of which visible light is only a part, and a narrow part at that. So this very narrow part of the electromagnetic spectrum, with wavelengths ranging from 400 nanometers, a very purple light, to 750 nanometers, a very red light, these wavelengths represent what our eyes can see. Now, if we go to smaller wavelengths than 400 nanometers, we get into the ultraviolet region, and of course we can't see ultraviolet light. And if we keep going to smaller wavelengths, or higher frequencies, we get to the X-ray region, and even smaller, we get to gamma rays, which are part of the electromagnetic spectrum. On the other hand, if we are at red light 750 nanometers and consider longer wavelengths, we first get into the infrared region, which we cannot see with our eyes, then the microwave region, and then radio frequency. Wavelengths are very long, so radio and television waves have very long wavelengths. Now we're going to talk about the ways that particles and waves act differently. We've all had the experience of taking a pencil or a stick and putting it into water, and it appears as if the pencil, for example, bends in the water. The path of a beam of light as it travels into a different medium bends. When we go from air to water, the light travels at a different speed in the different medium, and it causes this phenomenon called refraction. Now, this is quite different than the behavior of a particle changing media going from air to water. The particle continues on its arc downward in an unbroken line, whereas a wave hitting a different medium bends at an angle of refraction. There's a distinct way that waves and particles behave differently. That's called refraction. There's another way as well. If we take a handful of sand and throw it at a barrier that has a slit in it, sand particles that are on line with the slit will pass right through, but the other sand particles will hit the barrier and fall. But the sand particles that go through the slit will continue in a straight line. Waves, when they hit a slit, will begin to form a series of concentric arcs on the other side of the slit. That process is called diffraction. We've all seen this in bays or regions of water where the water has to go through a slit, and then we see these series of concentric arcs in the water. Another thing that waves can do is that they can interfere with each other either constructively or destructively. Here we have two sound waves depicted, but one is just a little bit smaller wavelength than the other. This bottom one has a slightly different wavelength. And what that does is that it causes the waves to oscillate in their relationship to each other. Here, both waves are aligned and you would have constructive interference. Then as the wave shifts, we get to a point where the waves are canceling each other out. So this manifests in a sound wave. Just listen to this. This represents two tuning forks, one which has a very slightly different wavelength than the other one. And we strike them both at the same time. So that warbling is characteristic of constructive and destructive interference. If light waves pass through two slits, you can get this effect of constructive and destructive interference. Where the waves are in phase, there'll be a bright line or a bright point. Where waves are out of phase, there'll be a dark line. And so that's characteristic of a wave. Now, when a solid object is heated to about 1000 Kelvin, you have a soft red glow. You heat it up to 1500 Kelvin, it gets brighter, and you have an orange glow, something like toaster coils. And greater than 2000 Kelvin gets very bright and very white, white hot. This phenomenon is called blackbody radiation, and classical wave theory fails to predict these wavelengths. In 1900, Max Planck developed a formula that did predict these wavelengths of blackbody radiation. Delta E equals NH nu, where delta E is the change in energy, N is a positive integer, which he called a quantum number, and nu is the frequency of the wave. H is Planck's constant, 6.626 times 10 to the minus 34 joules seconds. Planck's idea was that although light was a wave, these waves could gain or lose energy only in finite amounts related to their frequency. Planck called these lumps of light energy quanta, from the Latin word for how much. Later, the term photon was applied to these particles of light quanta. So if Planck's formula was delta E equals N times H times nu, and we've already seen how nu, the frequency, equals c, the speed of light, divided by the wavelength lambda, can you write Planck's formula using wavelength instead of frequency? Turn off the playback and see if you can write that. Okay, you should have come up with something that looks like this. Delta E equals the quantum number n times Planck's constant times the speed of light divided by the wavelength. So, as the wavelength of light increases, what happens to the energy of the light? If this number in the denominator gets bigger, what's going to happen to the energy? And if you think about it, we have an inverse relationship between wavelength and change of energy. And as the wavelength gets bigger or longer, the energy becomes less for that particular wave. So here's a question. Calculate the energy change of one photon of UV light, ultraviolet light, with a wavelength of 100 nanometers. And here are the two equations that you need and Planck's constant. Can you end up doing this? Turn off the playback, see if you can get it, and then come back to us. Here is the equation of delta E using wavelength instead of frequency. In Planck's equation, we get hc divided by lambda, and therefore plugging in h, Planck's constant, times c, the speed of light, divided by the wavelength that was given to us, 100 times 10 to the minus 9 meters. We have to use meters here because speed of light is in meters. So you can't plug in nanometers down here. Meters won't cancel out that way. That equals 2 times 10 to the minus 18 joules. We saw before how light behaves as a wave in refraction and diffraction. But there are experiments that can be done and phenomena that can be seen where light does not behave according to classical wave theory. One of these is the photoelectric effect. It's caused when electrons are emitted from the surface of a metal when it's exposed to light. Whenever you walk into a 7-Eleven and the buzzer rings, it's because you broke a beam of light as you passed through the door, and that completed an electric circuit, and the buzzer rang. Now, classical physics said that only the intensity or the amplitude of the light caused the electron to be dislodged. But experiments showed this was not the case. The light had to be of a threshold frequency, a certain wavelength or smaller, before the electron was ejected from the metal. Below this frequency, nothing happened, regardless of the intensity of the light. Now let me read this from your book. In 1905, Einstein proposed a bold explanation for the photoelectric effect. Light energy must come in packets. According to Einstein, the amount of energy, E, in a light packet depends on its frequency, nu, according to the equation E equals h nu. Unlike classical theory, in which light was viewed purely as a wave whose intensity was continuously variable, Einstein suggested that light was lumpy. From this perspective, a beam of light is not a wave propagating through space, but a shower of particles, or photons, each with an energy h nu. So, depending on the experiment, light had wave character to it, or it had particle character to it. And maybe the best way to show you that is with an analogy to sound waves. This equipment, a stable oscillator, a power amplifier, and a horn driver, will allow us to demonstrate an analogy to the idea that the energy of light is proportional to its wavelength. This beaker has a certain natural oscillation that we can hear by tapping its brim. The beaker is positioned on a rubber pad in front of a hole from which the sound emerges. First, we will select a frequency that does not match the oscillation frequency of the beaker. Even as we turn up the volume, we see that the sound has little effect on the beaker. Now let's select a frequency that matches the oscillating frequency of the beaker. If we use a strobe light, we can see that the beaker resonates from these sound waves. Now as we increase the volume of the sound, we can observe the effect that only this specific wavelength of sound has on the beaker. Now most of us have had the experience of taking a white light and passing it through a prism and then seeing a rainbow. Red, orange, yellow, green, blue, indigo, and violet. All the colors that we can see. Mr. Roy G. Biv, as it's called. But what you might not know is that if we take certain elements like hydrogen and put them in a tube and pass electricity through that element, it begins to glow and put out a light. And if we take that light, put it through a slit and then a prism, we do not get the full range of colors that we're used to seeing with white light. Instead, we get certain bands of color called a line spectrum. And each element has its own unique line spectrum. Here's hydrogens, here's mercury, here's strontium. So hydrogen has a red line, a blue line, a dark blue line, and a violet line. Helium has other lines specific to it. It has a red line also, but of a different wavelength. It has a telltale yellow line, very characteristic. The interesting thing about helium was that it was discovered first by analyzing sunlight before it was actually discovered on Earth. the spectrum showed up and they realized that no element that was known at that time had this particular line spectrum. And so they named this element after the Greek god for the sun, which was Helios. So helium comes from Helios. There's another way that we can see a similar effect, and that is if we take white light and pass it through a tube containing a particular element, and take the light from that and pass that through a prism, and again we see the colors of the spectrum with a big difference, that in each position where previously we had a line of color, now we have a dark line at those very same positions, at those very same colors. Those spectra are called absorption spectra, because these particular wavelengths are being absorbed by the atoms of the element and are no longer in the light, so they appear as dark lines at those positions. Here's the solar absorption spectra, and you can see again the dark lines. These particular ones I've marked correspond to the hydrogen emission spectra lines. And that is the first indication that the sun was mostly hydrogen. But there is this very bright line here in the yellow that hydrogen does not have, so that corresponds to helium, which is also part of the sun. Niels Bohr was a Danish physicist who came up with the first model to explain hydrogen line spectra. And while it worked well for hydrogen, it didn't account for elements beyond hydrogen. He suggested a planetary model where there were a series of concentric orbits around the nucleus that the electron could inhabit. And when the electron made a jump or a transition from one orbit to another, it would absorb or release energy as light. So think back, we passed electricity through a discharge tube. The electrical energy would be absorbed by an electron in hydrogen's ground state, n equals 1, and that electron could jump to a higher energy state. It could jump to n equals 2, or n equals 3, or 4, or 5. So it would jump to these higher energy states. It could not exist anywhere in between. It could only exist in these quantized energy states. And when that electron fell back down again to one of the lower energy states, it would release the energy as light of a specific color. So for example, an electron falling from n equals 5 to n equals 2, going from a higher energy state to a lower energy state, would release a violet light with a wavelength of 434 nanometers. An electron jumping from n equals 3 to n equals 2, a much smaller jump, would account for less energy and would release the red light with a wavelength of 657 nanometers. So energy was released when electrons fell from higher energy states to energy states or orbits closer to the nucleus. They would release specific, discrete amounts of energy as specific wavelengths of light. Absorption spectra worked a little differently. Remember that absorption spectra were caused when we take white light, pass it through the element, and then pass that light through a prism, and we get the whole spectrum devoid of certain spectral lines, black lines. Now, that's caused when the white light passes through the element and some of its energy is absorbed by electrons, making jumps from a lower energy state to a higher energy state. So when the electron jumps from n equals 2 to n equals 5, it's going to absorb light with a wavelength of 434 nanometers. And when it jumps from n equals 2 to n equals 3, it's going to absorb a red light at 657. So it's going to remove those wavelengths of light, and what we see then will be all the remaining wavelengths of light that were not absorbed in passing through the element. So far we've been looking at line spectra within the visible region of the spectrum, where electrons are making jumps from higher energy states down to n equals 2. So this is called the visible series. But there's also an ultraviolet series and an infrared series. In the ultraviolet series, electrons are jumping from higher energy states all the way down to n equals 1. The energy produced is so large that the light that is emitted is in the ultraviolet region of the spectra, a region of higher energy than visible light. Whereas electrons making jumps from higher energy states to n equals 3 produce energy which is less than that in the visible region, in the infrared region of the electromagnetic spectrum. If you look at this energy chart of the orbit versus energy, you see the reason for this. The jump from n equals 2 to n equals 1 is a considerable amount of energy. And as you go to higher energy states, the energy difference between the orbits becomes increasingly smaller. So simply shifting from n equals 2 to n equals 1 results in a lot more energy in the light that's being given off by the electron making that transition. We've said that the Bohr model only worked for the hydrogen atom. It couldn't predict or explain the line spectra of elements beyond hydrogen, helium, mercury, neon, and so forth. None of these could be explained by the Bohr model. And therefore, it was realized that much work still needed to be done in order to understand what the electron was doing in an atom. It was realized that if light behaved mostly as a wave, but in some experiments showed particle character, like in blackbody radiation or the photoelectric effect, these explained by quantized packets of photons, could electrons, thought to be particles, exhibit wave character? De Broglie was a scientist who had two equations to work with: E equals mc squared, Einstein's equivalence of energy and mass, and Planck's equation, E equals h nu, or hc over lambda. So if he made these two energies the same, could he have an equivalence between mass and wavelength? Can you solve this, putting these two equations equal to the same thing, therefore equal to each other? Solve that for lambda, for wavelength. And what do you get? Louis de Broglie in 1924 first proposed the wave nature of the electron, associating the electron's wavelength to its kinetic energy. Lambda equals h divided by the mass times the velocity of the electron. De Broglie suggested that all matter has wave character, or wave properties. This concept is known as wave-particle duality, or the de Broglie hypothesis. Now, if that's true, if electrons have considerable wave character because their mass is so small, is it possible to diffract electrons? Like waves undergo diffraction, can electrons undergo diffraction? Are there experiments that show that electrons can be diffracted? And that's exactly the basis of the Davison-Germier experiment in 1927. This photograph shows a diffraction pattern caused by electrons, confirming de Broglie's idea that electrons have considerable wave character to them. Let's use de Broglie's equation to come up with the wavelength of an electron, traveling with a velocity of 2.65 times 10 to the 6 meters per second. We have the mass of the electron, we have Planck's constant. Can you calculate for me the wavelength in nanometers of an electron with such a velocity? Okay, so what you should have is something that looks like this, and you plug this into your calculator and you'll end up with 2.74 times 10 to the minus 10 meters, which is the wavelength, or 0.274 nanometers. Now it's time for you to meet the famous Dr. Quantum.
And here we are, the granddaddy of all quantum weirdness, the infamous double-slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So, when we throw things, that is, matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter, through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So, they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits, and it goes through neither. And it goes through just one, and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. And it was here that physicists stepped forever into the strange netherworld of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
Now, in the real world, it was a laser beam that was the instrument used to detect the electrons, and which caused the electron to revert from wave behavior to particle behavior. This experiment and others pointed out the futility of observing within the quantum world. Any observing tool, such as electromagnetic radiation, has sufficient energy to interfere with the electron and change the behavior of the electron. This idea became codified in the Heisenberg uncertainty principle. One cannot know both the position and the velocity of an electron. This means that you cannot assign electrons to orbits as Bohr did. Instead, much more progress was made by treating the electron as a wave. Let's take a look at what is known as a standing wave and its behavior.
This device is designed to help us understand the nature of a standing wave, which will form when this string is spun by two rotating motors at either end. Before we proceed, let's review some basic wave terminology. A node is a point where the wave switches from a positive amplitude to a negative one, where the string does not move. This wave has two nodes between the nodes at either end. The amplitude of the wave is the wave height. The wavelength is any point in one wave to any similar point on the next wave. Crest to crest or trough to trough is considered a wavelength. The distance between consecutive nodes is always the wavelength, lambda divided by 2. If we manipulate the string, we can change the wavelength. Until the wave snaps into the lower harmonic, its movements are chaotic. Now the wavelength has been lengthened, so there is 1/2 a wavelength between the ends instead of one wavelength. Manipulating the machine, we can generate a standing wave with 0 nodes between the ends. This wave is called the fundamental wave and is the first harmonic. We say a standing wave has a quantized nature because it can be set to have only whole numbers of nodes. A wave will have 0 nodes, or 1, or even more, but never fractional numbers of nodes. For standing waves, because the boundaries of the wave are fixed, only certain specific wavelengths are possible, only those that generate a whole number of nodes.
Now we've learned that a wavelength is the distance from one point on a wave to an equivalent point on the next wave, crest to crest or trough to trough. So for A, B, and C, what is the number of wavelengths shown for each standing wave? For A, B, and C. Well, for A here, this is 1/2 of a wavelength. For B, here's a point at the 0 crossing going up, and the next point at the 0 crossing starting to go up. So this whole distance, B, would be 1 wavelength. And for C, therefore, we would have a wavelength and a half. Now, points at which the wave does not move are called nodes. The 2 points at either end of the string are nodes. Alternate nodes are points other than the ends where the string does not vibrate. How many alternate nodes are on each of the standing waves? Well, here's 1 in B. A doesn't have any. B has 1, and C has 2. Now, according to classical physics, particles move in a path determined by the particle's velocity, position, and forces acting on it. This is known as determinacy, definite, predictable future. But because we cannot know both the position and velocity of an electron, we cannot predict the path it will follow. So this would be called indeterminacy, with an indefinite future, and we can only talk about probability, about what's going to happen. The best we can do is describe the probability that an electron will be found in a particular region using statistical functions. It's a little like baseball. The path of a ball thrown by a pitcher can be calculated knowing factors such as the velocity and the starting point. So this is an example of determinacy. However, when a bat hits a ball, multiple factors influence the path of the ball, and we can only come up with a probability distribution map as to where the ball is going to end up after it leaves the bat. A special equation called the Schrödinger equation can be applied to the wave behavior of electrons to give allowed energy levels of the electron, as well as provide regions of probability of where the electron exists. These regions are not called orbits, they're called orbitals, regions in space where electrons may be found. The Schrödinger equation uses a wave function, psi, and calculations show that the size, shape, and orientation in space of an orbital are determined by 3 integer terms in the wave function. These integers are called quantum numbers. There's the principal quantum number n, the angular momentum quantum number L, and the magnetic quantum number m sub L. The principal quantum number n characterizes the energy of the electron in a particular orbital and corresponds to Bohr's energy levels, n equals 1, n equals 2, n equals 3, and so forth. So n can be any integer equal to or greater than 1. The larger the value of n, the more energy the orbital has. Energies are defined as being negative. An electron would have E equals 0 when it completely escapes the atom. The larger the value of n, the larger the orbital. And as n gets larger, the amount of energy between orbitals gets smaller. We've talked a little about this when we looked at the energy levels in Bohr's model, but it also applies here. N equals 1 is of the lowest energy. Again, it has a negative number, minus 2.18 times 10 to the minus 18, and there's a big energy gap to get to n equals 2, with an energy of minus 5.45 times 10 to the minus 19. Then a smaller gap to n equals 3, and a smaller gap still to n equals 4. Now the L quantum number primarily determines the shape of the orbital, and L can have integer values from 0 to n minus 1. Each value of L is called by a particular letter that designates the shape of the orbital. So when L is 0, we're talking about s orbitals. And these have a spherical shape. When L is 1, we're talking about p orbitals. And the shape resembles 2 balloons tied together at their stems. When L equals 2, we're talking about d orbitals, which resembles 4 balloons tied at their stems. And finally, when L equals 3, we're talking about f orbitals with 8 balloons tied at their stems. So in this picture, what we have is a spherical orbital, and then we have kind of this dumbbell-shaped orbital, 3 of them. And which is the s orbital? Well, the s orbital is spherical, so it's this one. And if we did a probability plot of where the electron could be found within this shape, we see that the density of dots is proportional to the probability density. And as we get toward the edge, the probability of finding this electron dissipates. And here's another way of showing the probability density as a graph. When the L quantum number equals 1, we're talking about p orbitals. And each principal energy state above n equals 1 has 3 p orbitals. These are given quantum numbers of -1, 0, and +1. And they kind of look, again, like these dumbbell shapes. At the center, one would find the nucleus of the atom and 0 probability of finding an electron. In an actual atom, these 3 orbitals would be superimposed on one another. They're just separated here so you can see them clearly. This is the second lowest energy orbital in a principal energy state. S is the lowest energy level. When L equals 2, we're talking about d orbitals. There are 5 of those. And when L equals 3, we're talking about f orbitals, and there are 7 of those. I'm not expecting that you're going to understand any of this. When we get to Chapter 8, all this will fall into place, and you'll have a much better idea of what this quantum theory is all about.